In this video, we're going to start to talk about free fall and what it means for an object to be in free fall. And the main idea is that the acceleration of an object in free fall is due to gravity alone. And so this is when only gravity is acting on the object. The two essential questions that we're going to answer in this video are what is free fall acceleration and how do objects move in free fall? So this all started back with a guy in the 16th century called Galileo. And before Galileo, everyone subscribed to the idea that Aristotle propagated, saying that whenever you drop something, the heavier it is, the faster it'll fall. So Aristotle felt that if you had two objects, one heavier than the other, and you drop them, the heavier object would hit the ground first. And this is a widely accepted view. Except Galileo came along and he thought that maybe this wasn't quite true, and he had a famous experiment of dropping things off the Leaning Tower of Pisa and to show the general public that no, things with different masses do in fact fall at the same rate. And he had a bunch of different experiments that he conducted to actually measure the acceleration due to gravity. And the interesting thing is he did this without any way of keeping time. Back then, they had no stopwatches, they had no clocks, they had nothing to keep time. So he was very inventive in the way he did this. So the vocabulary that we're going to look at here is the term free fall. That's going to be something we're going to use and what that actually means, and free fall acceleration. So let's imagine that we have a baseball that is hit directly up, straight up, perpendicular to the ground. And let's say it's launched off at 20 meters per second. Well, we all know as the ball goes up, as time goes on, the velocity will decrease until eventually it stops for a moment. Because then after it stops, it's going to eventually start to fall back down. And so we observe that the displacement gets bigger and bigger and bigger until it reaches this maximum point here. And then at that maximum point, it will start to fall down and the displacement will decrease because it's coming back to where it was launched. And this is happening because it is undergoing acceleration. We can see that from the displacement versus time graph. Now, this is just a zoomed in portion of the displacement versus time. Basically, it's talking about this portion right here. But we see we have a curve. This is a parabolic curve. And so that's going to translate to a linear curve in the velocity versus time graph. And if there's a line here, that means that there is a slope right here. And if there's a slope, that is the acceleration. So this ball must be accelerating. And in fact, it is accelerating. The acceleration that it's going through is called free fall acceleration. Free fall is what we call the motion of an object when gravity is the only significant force acting on it. So in the ball, after the ball leaves our hand, the only force acting on it is gravity. So we say that ball is in free fall throughout its entire path, up and down. The acceleration of an object due to only the effect of gravity is known as the free fall acceleration. And on Earth, we pretty much have an average free fall acceleration everywhere on Earth, and that is 9.8 meters per second squared, directly towards the center of the Earth, which on the surface that translates to perpendicular to the surface of the Earth. So what this means, if we were to drop a hammer and a feather, they would both hit the ground at the same time. Now, you might be saying, wait a minute. I know whenever I drop a hammer and when I drop a feather, the feather takes a lot longer to hit the ground. Now, we observe that in our world right now because of air resistance. And we're not going to talk about air resistance much in this course, but if we were to actually drop without air, so say we're in the vacuum of space on the moon, or if we had this mythological Earth with no atmosphere or air at all, if we were to drop those, then yes, they would fall at the exact same rate. And that rate of change of their velocity is the acceleration due to gravity, which is 9.8 meters per second squared. So we're going to use this and the equations that we got from the last section to do some math problems here. The nice thing is just the acceleration in all of our equations is going to be baby g, which is 9.8 meters per second squared. And so anytime we have acceleration in free fall, this is always the value of a. All right, so let's look at a situation here. Let's say we're on one of those free fall rides at an amusement park, whether it's at Cedar Point or even Waldameer has one of those, where you just drop in free fall for a little bit. So let's say we are dropping in free fall for a time of 1.5 seconds. So we go all the way up to the top of the tower, and then it releases us, and we drop for 1.5 seconds. And we want to know, what is our speed down at the bottom? What's our final speed? Well, in order to answer this question, we have to look at what assumptions can we make. What are some valid assumptions? Well, first off, we can make a valid assumption that our initial velocity at the top before we are released is going to be 0 meters per second, because we're just going to be stationary up there, chilling up at the top, and then all of a sudden it's going to release us. So we're not going to be moving, and then it releases. It doesn't push us down, it just lets us go. So our initial velocity is 0. Well, the other assumption we can make, this is in free fall, and so the only acceleration or the only outside force that's acting on this ride is going to be the free fall acceleration, or an acceleration of 9.8 meters per second squared. So this gives us all of our given information, knowing that we want to find this right here. Okay, so what equation relates acceleration, final velocity, initial velocity, and time? That is our average acceleration equation, where we take the change in velocity divided by the time, and that gives us our average acceleration. Well, we know this, we know this, we know this, and we want to find this, so we can just do a little algebra and solve and get our final velocity to equal the initial velocity plus the acceleration times time. Well, we know the initial velocity is 0, so we don't even have to worry about that. And we can say the final velocity is equal to 9.8 meters per second squared times 1.5 seconds. And if you do this, you get about 15 meters per second. And so to give you an idea of what that is, it's around 33 miles per hour. So if you're dropping for 1.5 seconds, then you reach a speed of about 33 miles per hour, or 15 meters per second. Now, let's say we wanted to find how far did we fall. So what is our distance? So what is delta x in this case? Well, that's where we want to use that equation that had delta x solved for us, where it's the initial velocity times time plus 1/2 the acceleration times the time squared. Well, once again, the initial velocity is 0, so that goes away. So the distance that we fall here, our displacement, is going to be 1/2 9.8 times the 1.5 squared. And that gives us about 11 meters. So that means we fell about 11 meters and we reached a speed of 15 meters per second. Now, obviously this ride right here is not all that thrilling. It's kind of short and not very long, but that's just an example of how we can use free fall and these equations. So hopefully in this video you were able to see what is free fall acceleration and how do objects move in free fall, and you understand those two vocabulary terms.